So let's try to make connection for delta delta 180 degree. Okay, this we made, and we have seen that this the relative phasor angle between the primary side line voltage and secondary side line voltage is exactly 0. So we can say that this is delta delta 0 degree connection. So can we make delta delta 180 degree connection? So I'm just redrawing the transformer in another way of doing it, just to just to explain it in a little simpler way, to make the connection a little simpler to remember as well. Okay, so delta delta, let's say this is for the primary side I am drawing. So primary side, this is A2, or I would say A1, A2 here, and the dot is here. Similarly, B1, B2, C1 and C2. And for the secondary side, let's say we have the winding. So let's say this is A1 and dot is here, and this is A2. This is B1, dot is here, and this is B2, and this is C1, dot is here, and this is C2. Okay, so in the previous connection we have seen that, okay, the supply voltages are here. Let's say A, B and C was here. A, B and C as supplies are coming. Okay, so what we did was we have connected A2 with B1, right here, right? See, A2 with B1, right? So A2 with B1 and B2 with C1, and then this C2 was actually connected with A1, and we have given this supply here, and from here we have given the supply to B, and from here we have given the supply to C1. Okay, so if you see the line voltage here, that is VAB or VASBS, that is nothing but the potential difference between this point and this point, right? So the line voltage which is appearing here is the phase voltage across this transformer. Okay, so this was for the primary side. So similar connection we have kept. Now let's try to make it for 180 degree connection. Okay, so let's see, here I was connecting A2 with B1. This time what I will do is I will connect A1 with B2 and B1 with C2. Okay, and this C1 and A2 I will connect here. So earlier you were tapping power from A1, right? So let's say if you tap power from A1 and B1, let's say A you have marked here and B here, let's say. So actually your phase B will read the line voltage AB, which I don't want. What I want is, so I would be having the power here. So this is A for the source, for the load. This is B phase and this is C phase. So this time you see the voltage here appearing across the this line voltage AB, VAB. Okay, so if this time if you'll see, VAB would be the potential difference between A2 and A1. Earlier here if you'll see, the line voltage between A and B, this voltage here was A1 and A2, right? Terminal A is at A1, but this time terminal A is at A2. Okay, and B is connected with B2 as well as A1. So this time we will get a reverse voltage, right? So VAB would be, I would say, VA2 minus VA1, which is nothing but minus of VA1 A2. Okay, so that's how for the other phases also you can see. So this will make you delta delta 180 degree. Okay, but mind it, so obviously these are the transformers. I'm like for single phase transformers I am just discussing, but this is equally valid for three phase transformers. Okay, any single unit three phase transformer. Now let's say someone says, no, I don't want to connect in this way, because this is just a matter of connecting in a circular way where the closed path is there, but that is not the case. Let's say someone does not take care of the dot and just directly wanted to connect the as per his own wish and does not follow the these dot conventions there. So see then what will happen. So let's say these connections has not been made. Okay, so what he does is, let's say for 180-degree connection only, but what he does is, let's say A2 he has connected with here and A2 is connected with B1. Okay, and but this time instead of connecting B2 with C1, what he does is he made it to C2 and he wanted to short this. He wanted to connect this A1 and C1. Is this a valid connection? Is this a valid connection? So for that we can short a delta connected circuit, two phases, only when there is a net potential difference is 0. So let's try to find what is the potential difference between VA1 and C1. VA1 and C1. Okay, what is this? So VA1, C1, if it sees, so as per this dot convention, if voltage is here in this direction, this voltage would also be in this direction. This voltage is also in this direction, and this voltage is also in this direction. Okay, so let's say VA1, C1 we want between this point to this point. So we'll write a KVL for it. VA1, C1 minus of, because there is a potential drop here. So increase in the potential I will take positive. So negative. So decrease in the potential. VA1 and A2 is a potential drop. So that I will write at VA1, A2. Then from here as well, if you'll see, so this is a drop of V, B1, B2. Okay, and this is okay, and here you see, here it is an increase in the increase in the voltage. So that is plus of VC1, C2 and 0. So VA1, C1, if you see that it would be VA1, A2, VB plus VB1, B2 minus of VC1, C2. And obviously we know that then in this condition the sum won't be 0. Actually not equal to 0, right? VA1, C1 is not equal to 0, and you can even compute the magnitude of it. Okay, so if we are shorting, let's say if we turn it now, obviously the potential difference is not 0, and there would be a huge amount of current because the winding resistance is almost 0. So there would be a huge amount of current and the winding will get damaged here because of the circulating current here in this branch, in this loop. Because of the circulating current, you have shorted without any external resistance, you have shorted these potential points A1 and C1. Okay, so it will damage the winding. So in a star connection, if someone had made a mistake in connection, then also he will get a voltage, but line voltage would be reduced. That unbalanced voltage supply would be there, right? That's what we discussed. We discussed here, right? Here, see. But in delta connection, one has to ensure about the dot connection. Otherwise, the chances of creating a fault, dead fault, or short circuit fault would be there. Okay, so you have to ensure about the dot convention. Okay, so this was about delta as well, and in delta connection also we have seen that the transformation ratio is also for the phase voltages and the line voltage, they remain same. That is 1:2. I would say A is to 1 only. Okay. Now we will discuss about star and delta connection. So in a star delta connection, the primary side is delta star connected. So I will just draw a little simpler one. Let's say A1 here, capital A1 here, and A2 here. This is B1 and this is B2 here, and this is C1 and this is C2 here, all connected at a neutral point. So that will make a star, and this has been connected with, this is A phase, this is B phase, and this is C phase here. I could have drawn B here as well. That would not be a problem, because phasor diagram and the winding representation does not have a correlation. Okay. So, and let's try to make it for the delta connected one as well. The secondary side of the transformer has been made delta connected. Let's say this is A1, because we were tapping power from A1. So I will say, let's say A1 here. Okay. And this is A2. This is B1. B1. This is B2. This is C1. This is C2. So at A1, we would be having the potential in this direction. Here the potential would be in this direction towards the dot, right? So A1, A2, so the dot would be here, potential would be in this direction. Similarly for B1, B2, so potential is in this direction. For C1, C2, the potential is in this direction. Okay, this is my phase A, this is my phase B, and this is phase C. Okay, if you see the line voltage here, VAB is nothing but the phase voltage VA1A2, right? Similarly, line VC, the line voltage VC here is the phase voltage which is appearing between B1 and B2. Okay, so let's say the turn ratio for each phase is A:1. A:1 is the turn ratio of each phase. Okay, so this time the primary has been connected into star, and the secondary has been connected into delta. So let's say the phase voltages, the source voltages, the phase of it is voltage V. So obviously the line voltage which will appear here is √3V. Okay, for the source, line voltage is √3V, and for phase A, let's say if I want to write VAB, if I want to write, that would be √3V at an angle of 30 degree. VBC would be √3V at an angle of -90 degree, and VCA would be √3V at an angle of +150 degree. So obviously, if you see if you see at the secondary side of this transformer, what is this voltage? VA1, A2. Okay, that is the voltage at the secondary of this transformer 1. Okay, VA1, A2. So this voltage is nothing but, if you see the turn ratio, as per the turn ratio, VA1 upon A2, VA1 A2 upon V capital A1 A2. So capital A1 A2 I am taking it for the primary side, and smaller A1 A2 I am taking for the secondary side. Okay, so this phase voltage and the phase voltage appearing, which is appearing here, they would be 1 by A. The ratio of it would be 1 by A as per the transformation ratio. Okay, so we can write that VA1 A2 would be VA1 A2 by 2. But this VA1, A2 is what? This is the phase voltage, right? This is the phase voltage which is coming here, and phase voltage here, if you'll see, that would be the magnitude of it. The magnitude of it would be 1 by root 3 times of this, right? And the angle would also be at 0 degree, right? So the phase of it would be, we can write as, sorry, this is A actually. So in terms of V, if I want to write, which was the phase voltage of the source, okay, then this would be V upon A, and that also at an angle 0, because here the phase voltage, if you see, VA1, A2 would be root 3 upon divided by root 3 at an angle 0, right? This would be V angle 0. So this is V by A at an angle 0. So the secondary side voltage would also be, the phase voltage of it is this ratio V A1, A2, and this is the phase voltage, right? So for the secondary side, if I write the line voltage, okay, which is VAB, right? Line voltage VAB, this is same as this phase voltage, right? Which is V by A at an angle 0, right? So if we want to find the line voltage here, let's say the transformation ratio of the line voltages of the primary side and the secondary side. So primary side line voltage is, let's say, VAB upon the secondary side line voltage is VAB. If I want to find the transformation ratio, you'll see this value would be VAB is root 3V, okay, upon, okay, because I want to write the transformation ratio, so I'm not bothered about the angle here. So that's why I'm taking the magnitude only. So root 3V, which is the line voltage here of the primary side, and the line voltage at the secondary side would be V by A, okay. So which is nothing but root 3 times of A. So here in star delta connected circuit, what you can see is the transformation ratio of the line voltage of the primary, upon line voltage at the secondary side, okay, they are root 3A. So P stands for, or for primary I used to write 1, so I would say 1 degree, and this is 2 degree. That means for the primary side, and this is for the secondary side, root 3A. And let's say phase voltage VP, I'm writing for phase voltage of the primary upon VP of the secondary. If you will see, this is A by 1, this is root 3A by 1. So we have seen that in this star delta connection, at the star side, the turn ratio is, for the line voltage, it is inherently having higher ratio, higher values, right? So this kind of transformer is basically used to step up the voltage. Let's say at the generating station, what we want that transformer voltage, the generator voltage should be stepped up. So this transformer is used there. So delta would be connected towards the generator side, and the star connection would be towards the transmission line. So transmission line will have inherently root 3 times the line voltage will inherently have this much of step up voltage, okay, root 3 times than the phase voltage is there, okay. So this is generally used and mostly used in the power system network to step up the voltage, okay. And let's see about the phasor diagram here. What would be the phasor relationship from the primary side line voltage and secondary side line voltage, okay. So we have seen that at the primary side, if we start with this, we assume that, okay, source phase voltage is this. So line voltage is at 30 degree. So what we have seen here, that the line voltage at the secondary of this transformer, delta connected one, this is at 0 degree here, right? And the line voltage here is at 30 degree. So that means the secondary of this transformer, I would say the line voltage of the secondary side of this transformer is lagging the primary side voltage by an angle of 30 degree, right? So see, there is a difference between VAB is at angle 30 degree and VAB at the secondary side is at angle 0. That means if I draw the phasor, let's say VAB at angle 0, let's say VAB here, okay, VBC, VAB, VBC and VCA here, then that's at the secondary of this side. What we'll see that because the phase voltage would be for this connection, a star connection, phase voltage would be lagging, right? The phase voltage would be lagging the line voltage by an angle of 30 degree, right? And this turn ratio we have seen is given for the phase voltages there. So phase voltage, if we would like to draw, the phase voltages would be this. For phase A, AB, this phase voltage would be 30 degree to this one, okay? And the same voltage is the line voltage as well, okay? So this is VAB. And what about VAB, or I would say VAB is nothing but VA1, A2, right? And VBC is connected between this point and this point. That means across B1 and B2, okay? So B1 and B2 would be 120 degree to it, right? So we will be drawing B1 and B2 here. So this is AB and this is equally VA1, A2. And what we have used here, A1 we have used for terminal A, right? And A2 we have used for B. So this is, so I would say A1 is here and A2 is here. Similarly, B phase, if you'll see, so B1 is connected to A2, right? So if this is B1, this is B2, and this is C1, this is C2, okay? So if you compare with this, the line voltage, and since the line voltage and phase voltage are same here, and if you compare this, actually this is lagging the line voltage of the secondary side is lagging the primary side with an angle of 30 degree. So this is a connection of, I would say, star YD minus 30, okay? So actually this is needed. Let's say if you are connecting a parallel transformer, like if you are connecting two transformer, why this is important? You will know, like at the terminals of it, what would be the phasor difference between the primary side and the secondary side. So you can easily use it for, let's say, for parallel operation of the transformer. Okay, so two transformer, if you want to parallel it, they should be from the same group as well. So the third value which I am giving it, that actually decides what would be the grouping of this transformer. Okay, similarly you can try for YD30, okay? You can try for YD30 as well. So even this connection is also possible.